Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 3rd, 2026, just over a week ago. It demonstrates that using the log probability of a reference answer as a reward signal is the most robust option for fine-tuning large language models, performing well on both verifiable math problems and open-ended tasks where binary rewards usually fail. The paper is titled Likelihood-Based Reward Designs for General LLM Reasoning. And as we'll see later, the results suggest this could be a universal recipe for post-training reasoning models. Table 1 breaks down the results on verifiable domains like math and deep-scale R. Focusing on the Llama 3B model in the top section, the greedy success rates show the log probability reward, in the third column, achieves about 43% accuracy, slightly edging out the base reinforcement learning baseline. A crucial difference appears in the perplexity scores, where the log probability method scores a low 2.2, drastically better than the 13.9 seen in base reinforcement learning, which indicates much more stable generation. However, there is a trade-off. When answers are sampled stochastically, the log probability performance drops significantly, likely because the model overfits to the single most likely path. Figure 1 plots these metrics over training steps, giving us a clearer view of the learning dynamics. In the top left panel for greedy success rate, we see that all reinforcement learning variants, shown in green and blue, quickly ramp up to match or exceed the black dashed baseline. However, the bottom left panel reveals the stability advantage. The green log probability curves plummet immediately to a low perplexity, while the black baseline stays much higher. Most curiously, the bottom right panel tracks the chain of thought length. Here, the green lines take a sharp dip early in training before recovering, which implies the model briefly tries to shortcut its reasoning to maximize the log likelihood reward. Moving on to non-verifiable domains, Figure 2 presents the learning curves for the QN 2.53B model on the Numina proof dataset. In the first two panels, the green log probability curves track closely with the supervised fine-tuning baseline, meaning they learn the target distribution effectively. Conversely, the probability-based reward, shown in dark blue, fails to improve at all. The critical finding, however, is in the rightmost panel. Here, the chain of thought length for the log probability models collapses almost instantly to match the baseline. This shows that, without a verifier, the reinforcement learning process simply eliminates reasoning steps to maximize the immediate reward. Well, Table 2 confirms this pattern across both Llama 3B and QN3B models. Looking at the top section for Numina proof, the perplexity scores for the log probability family, around 3.04, match the supervised fine-tuning baseline in the far right column almost exactly. This reinforces that in non-verifiable settings, the reinforcement learning signal converges to the same outcome as standard supervision. In contrast, the probability column shows no improvement over the base model, likely because the rewards are too sparse. Finally, the chain of thought length row explains the mechanism. The model collapses from nearly 500 reasoning tokens down to just 9, effectively abandoning the chain of thought to mimic the short, direct answers of the supervised baseline. Given that collapse, Figure 14 investigates whether we can artificially stabilize the reasoning process using penalties or auxiliary rewards. The four rows display different reward functions, but the story is consistent. In the rightmost column tracking chain of thought length, the purple lines flatline near 0, confirming the reasoning vanishes. In contrast, the blue trajectories show that adding length-based rewards successfully forces the model to generate hundreds of tokens. However, the middle column for perplexity reveals the cost. These longer chains often result in higher, or worse, perplexity, suggesting the model is just rambling to satisfy the length constraint rather than improving its reasoning. So Figure 21 digs deeper into the mechanics behind that reasoning collapse on the math dataset. It plots the chain of thought length on the x-axis against the log probability of the correct answer on the y-axis. The scatter plot reveals a distinct downward trend, marked by the black dashed line. As the inset box highlights, the global correlation is negative 0.45. This confirms that longer reasoning chains result in lower log probabilities, which effectively penalizes the model for thinking too long. Wrapping up, two takeaways stand out. First, log probability rewards provide a universal training signal effective for both verifiable math problems and open-ended tasks, removing the need for custom verifiers. Second, although the method often reverts to shorter answers in non-verifiable settings, it remains stable where other probability-based techniques fail completely. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.